Okay, so we're going to pick up an example in SI unit. This is example 8.3. So we're using the document ACI 211.1 R-91 review 2009. Okay. Yes. So, and this is example A2.1 in the document. Okay. So, this is the document we are using. Okay. Okay, so I hope you've got the documents with you. Example one. So there's an earlier example, same example presented in FA system. I hope you are on the right page 23.
Yes, yes, sir.
It is page number 23. Okay. So we are on page number 23. And this is example 1A 2.1 is the example. Okay. A 2.1.
Yes, sir.
All right, so the given data says that the required every strength will be 24 megapascal. So required average strength is 24 megapascal. Now, I need to clarify that this is not the designer specified concrete cylinder strength. This is not the FC prime. Okay. So FC prime, what do you expect? What should the FC prime be with respect to this? Should this required if the required is 24 megapascal? What do you think about the design value?
Be slightly more than
Really? What about the design value? If this would be required, so I would say it another way. If required is, for example, 30 megapascal, or let's say 20 megapascal, then what do you think about if the specified cylinder strength is about, let's say, 21 megapascal, then what do you think about the required average strength that you must obtain when you're constructing the project? It will be more. So it means that the specified value was something lesser than this, and there's a way to get this value. I mean, you can use either the previous data and use the standard deviation of the previous data, or you can use a simple value. I'm going to share that equation some other time with you. So right now, what we're saying is that this is the required average strength. This is not the specified cylinder strength. Specified cylinder strength is some value lower than this. Okay, so if required average strength is 24 megapascal, and the slump value that we require is 75 to 100 millimeters. This is also required value. Okay? This is the desired slump. Okay. Now, how do you pick this value? It depends upon the nature of the project, the nature of the structural element that you're going to construct. Okay. So if you expect a congested reinforcement, you would expect a more workable concrete. You would require a more workable concrete. Okay. If you have got better equipment, better vibrators, you may need smaller. You can work with a smaller slump, but generally speaking, you would need a slump around 50 millimeter or so. Okay? So this particular project says we need 75 to 100 millimeter slump. Okay? So the coarse aggregate that we're going to use has a nominal maximum size of. So the nominal maximum size of coarse aggregate is equal to 37.5 millimeter. Okay, and the dry body mass, actually we should say density of coarse aggregate is equal to 1600 kg per meter cube. Okay, so how do you get? So if you're given the aggregate, how will you find this term, nominal exercise of aggregate? How will you figure this out? What is this value for a given aggregate? For the aggregate sample, how will you figure this out? See analysis. And how will you do this?
Bulk test.
Bulk density. You got to perform bulk density test. Okay? So, you get this data from that test. Okay? 1600 kg per meter cube. So cement that we're going to use is a type 1 cement, which means it's an ordinary Portland cement, OPC. Okay? Specific gravity of the cement is 3.15. If you're given this value, it's fine. I mean, if you can find this value in the lab, you can, I mean, if you have the equipment, you can find it. Otherwise, you can assume it to be 3.15. Okay? Specific gravity is, a ratio of two densities, density of the material to the density of water. So you got the unit cell number. Fine?
Yes.
Alright, so what else is given? The specific gravity of the aggregates. Okay, so let's write this down in tabular way. So we have got the coarse aggregate and we've got fine aggregate. Okay, so coarse aggregate is, so here we are going to write the properties. So first let's write down the specific gravity. So it is specific gravity, okay? Specific gravity of coarse aggregate is 2.68. So if you're given an aggregate sample, you can find out its specific gravity, okay? Specific gravity of coarse aggregate. And its absorption is 0.5%. Okay? You can also find the absorption. It's actually the same experiment in which you find the specific gravity and the absorption. So you get these values usually in a single experiment. Okay? And then the fine aggregate has a specific gravity of 2.64 and its absorption is 0.7%. Okay? And one more thing about the fine aggregate is its fineness modulus is 2.8. We don't need the fineness modulus of coarse aggregate. It's not something we require for coarse aggregate. We require it for the fine aggregate. How would you find this fineness modulus? Sieve analysis. Sieve analysis. So sieve analysis of coarse aggregate and fine aggregate, you have to perform these two tests. You have to perform specific gravity and absorption on both coarse aggregate and fine aggregate. Okay, and you have to perform dry body density of coarse aggregate. Okay, and if you can do this, otherwise you can assume it to be 3.15. All right.
Yes.
And these are the things you're going to choose based on your project. What is the specified FC prime? Based on that, you will choose the required average strength. Okay? The required average strength is usually 8.5 megapascal, higher than the specified value. Okay? So if the specified is about 17 or so, the required will be 24. Okay? So I'll give you that equation some other time, maybe at the end of the talk. All right. So we are going to. So what does that mixed design actually mean? At the end of the mixed design, we are going to have the proportions that in which we need to mix these ingredients: cement, sand, coarse aggregate, and water. Okay. So for these four ingredients, we're going to find their proportions. Now, step number one is let's go step by step. So step one is you can just list down the slump. Okay, slump is, although we have the data, we have it in the data, but that's how you execute the steps in the sequence. Slump required is 75 to 100 millimeters. Okay, and step 2 is to list down the nominal maximum size of aggregate. Coarse aggregate, of course. It is 37.5. So now step 3 is to decide the mixing water requirement. Okay? It is the estimated mixing water that needs to be decided. Okay? So how we decide this? We have to use a table. So please all go to the table number. I'm going to write it down for you. Table. It is table number A. So you go to page number 22, you find it on the top. A 1.6.3.3. Okay. And it says approximate mixing water. I hope you are on page number 22. On the top, you will see table A 1.6.3.2. Okay. And the heading is approximate mixing water and air content requirements for different slumps and nominal maximum sizes of aggregates in SI units. Okay. So there are two parameters, there are two input parameters for this table. Okay. So these are the two input parameters for this table, and that's why we list them down before going into the table in step number 3. Okay. So on this table, over here you see slump value, the slump. Okay. On this side you have the slump, and on this side you have the nominal maximum size. Okay. Nominal maximum size of force aggregate. Now our value is how much? 75 to 100, and that value is 37.5 millimeters. Okay, so you will go this way and then that way, and there you should be able to read the value for the nominal mixing water, for the estimated mixing water.
180.
So can you please read from the table what should be the estimated mixing water for it?
181.
How do you get it 165? Yeah, you have got two sections in the table. Let me clarify. The first one is for the non-air entrained. Okay. Non-air entrained concrete. And the second one is for the air entrained concrete. So we, if you want to write it, we are going to use type 1 cement, and the concrete that we are going to use is non-air entrained. Okay? Air entrained concrete is used for improving the resistance of concrete to freeze and thaw cycle. So we don't have any such problem. We're not expecting any such problem, so we're going to use the non-air entrained concrete. Okay? So we're not here, we're in this part of the table, the upper part of the table. Okay? So we are in this part of the table. So now if you can give me one more part.
181.
That is
81.
81. Okay? So this number is 181, and this is in kgs per meter cube of concrete. Let me explain this to you if you don't already understand it. What does it mean? So this is the net mixing water. Net mixing or just mixing water is enough, I can say. So this is the mixing water that we need. So mixing water required is estimated to be 181 kg per meter cube of concrete. What does it mean? If you're making 1 meter cube of concrete, you need to add 181 kg of water for the purpose of mixing. Okay, so that water should be available for the purpose of mixing. It shouldn't be going into the aggregate. Okay, I'll come back to this point when we're doing the final calculation, but you need to understand that this water is something you need for mixing only, shouldn't go into the aggregate. All right? And the other situation is when your aggregate is wet. So you have some water already on the surface of aggregate, and if the mixing water requirement is just 181, it means you actually add something less than this in order to make the actual mixing water equal to 181, okay? Because some of the water will be in that case coming from the surface of the aggregates. Okay? If there are there's free water available on the surface in that case, okay? So now, for this step we have done, mixing water requirement is 181 kgs of water. So this is kgs of water per meter cube of concrete. All right. So don't think it is a density. It is not a density. It is just the proportion, the content of water that you need. Okay. So kgs for water and meter cube for concrete. I hope you understand. If I need more slump, higher slump, the requirement will increase. Okay? And if the nominal mixing, if the maximum aggregate size reduces, again the mixing water requirement will increase. Why? This is clear. You need more slump, you got to add more water. Why do you need to increase the mixing water requirement for a small size aggregate?
Surface area.
The surface area will be more, and because you need to add more water to lubricate all of that surface. Okay? So there's going to be more resistance. So you got to add more water. Okay? Now, this is step number 3. Let's go on to the next step, step number 4. Okay, maybe I want to remove the same part. Are you done with this?
Yes, sir.
Because I want the data to be available. So I could just write step 3 was, the final output of step 3 was that the mixing water required is 181 kg per meter cube of water. Okay. Now step number 4 is the water cement ratio required. What water cement ratio is required? So what do you think? What should it depend upon? Water cement ratio of concrete. So water cement ratio, like what do you think it, like what, I mean this mixing water requirement was based on these two input parameters, depending on these two parameters. What do you think about the water cement ratio required? What should it be based on? What should it be, like what should be the input value for this table? Yes, required average strength. You need more strength, you need to have a lower water cement ratio. I hope that makes sense. If water cement ratio is high, means you have like more water and less cement. What does that mean? When the cement paste hardens, you're going to have, you end up with a lot of pores in that cement. Okay? So you're going to naturally have a weaker cement paste. Okay? So water cement ratio higher value means you have a more porous cement paste and that is a weaker cement paste. Okay, because the water is gonna evaporate excess water, which is not going to be used in the hydration process. It's gonna it's gonna make the concrete the cement paste for us. Okay, so next we are going to use one more table. Let me just list that down. So go to table. Uh, that is table A1.6.3.48. Okay, so go to page number page number 22 again. You should be able to find the table on the left. Okay, so here is the table. All right, and the table says relationship between water cement ratio or water to cementitious material ratio and compressive strength of concrete. Okay,
Yes, sir.
in SI system. So on this table you have got, on this side you have got compressive strength. There is the average required compressive strength. Okay, compressive strength in megapascal, 28 J. I hope you understand that. And on this side you have got water cement ratio for two different cases. One is for the non-air entrained, and the other one is for the air entrained. Because this is not our case, we're going to ignore this one. So non-air entrained concrete, and on this side you can see for 40 megapascal, you need to have a 0.42 watt cement ratio, and then it goes down to 25 megapascal, where it says you need 0.61 water cement ratio, and for 20 it says it should be 0.69. Okay. Now, what is our required average strength? 24. So we lie somewhere over here. Okay. So what do you do in that case? Sorry? Interpolation. You have to interpolate for this value. Okay? So, this is something, if you want to go with the X and Y symbols, you can say, for example, this is my X1, and this is my Y1, and this is my X2, and this is my Y2, and this is the X for which I need my Y. Okay? So now you need to go like that. Y is equal to, see? So Y is equal to the previous value of Y, which is Y1, okay, plus the slope. So what is the slope? Y2 minus Y1 over X2 minus X1. So it is 0.61 minus 0.69 over 25 minus 20. So this is the slope times the distance between, so how far have you gone? So the difference between these two values. Okay? So it is x minus x1. So x minus x1 will be 24 minus 20. Okay, so this y1 is, I'm sorry, 0.69. Okay. Can you please calculate? This is going to be something negative.
0.626 overall.
0.626. Okay, so 0.626, and if we want to limit ourselves to 2 decimals, what do you think we should do?
0.626.
0.63 is a more mathematical approach, but a more logical approach would be a low water cement ratio means high strength. Lower water cement ratio means high strength. So you better round it up onto the lower side. Okay? Although it's all trial calculations, but you may better round up to the lower side, 0.62. Okay? So what do you get at the end of step 4? water cement ratio to meet this requirement is expected to be 0.62. Okay, don't take it too hard and fast. Okay, so you can only say this is the expected. This is the one that should work. Okay, this is the best. This is your best guess. Okay, so water cement ratio at the end we have got so. So can I just remove this? Maybe sometime later. Okay, so water cement ratio for strength purpose is 0.62.
ये वाला नजर नहीं आता मुझे
I see you need that. Oh, okay, that's out of the way.
ये नजर आ रहा
Okay, so I'm gonna turn it for just a second so it gets recorded in the video and then I can. Okay?
ठीक
All right. अब आपने इसको ठीक करना है. It's fine.
है
All right. So, it is 0.62. Water cement ratio at the end is 0.62 for strength purpose. Okay. Now, concrete doesn't only need to be strong enough; it needs to be durable enough as well. Okay. So durability, let me tell you one thumb rule. A stronger concrete, generally speaking, a stronger concrete is expected to be more durable concrete. Okay? A weaker concrete is expected to be less durable. The reason behind the two things is one, the higher water cement ratio will give you a lower strength concrete. Why? Because you've got more pores in your water in the cement paste. Okay? And more pores in the cement paste actually means that the concrete is going to be more porous, and that means the sulfates, the chlorides, and any attacking material has got a better chance of penetrating the concrete. So you have got more durability risks involved. So water cement, so lower water cement ratio means higher strength as well as higher durability. Generally speaking, okay, all the durability has to do with a lot of other factors as well, but this is the general rule we're going to follow. Okay, so we're going to see if there's any more strict requirement on water cement ratio for durability. So let's go to table number A point. So you go to table. I hope now I can remove this one. So this is step for part B. This was step for part A for strength purpose, and then for the durability purpose. Okay. Now table A. So this is table A 1.6.3.4b. So what is this? It's on the same page, just to the right of the previous table, part A. Okay. So this is part B of the same table, just to the right. Okay. Now, this table has on one side it tells you the type of structure to choose, and then it also lays out some more conditions. For example, structure wet continuously or frequently and exposed to freezing and thawing, which means you're expecting a more attacking environment, more less friendly environment, should I say? Structure exposed to seawater or sulfates. So the more harsh is the environment you expect, you're going to have a lower water cement ratio. Okay? So we don't expect, and for this particular structure, for example, if it is given that there is no such exposure, there's no exposure, so there's no exposure to seawater or sulfates, if there's no exposure to freezing and thawing, and there is no exposure to, there's not going to be continuously wet or continuously frequently wet structure. It means looks like it's something indoor, which is, for example, it's at least not a bridge. It's not it's something that is not in a much harsh environment. Okay, so maybe just a beam indoor. Okay, maybe a slab indoor. Not expected to come across these environments. So we're not going to have any special limit based on those conditions. So the only criteria would be the strength that governs our final decision of water cement ratio. So water cement ratio, finally, I understand the final value, but it's something with final guess. This is the final guess. Okay? not the final value, but it's final guess. I would say it's final guess. Water cement ratio is 0.62. All right, now step 4 is done. Step 5 is simple. So if you remember, this was step number 3, final output. This is step number 4, final output. And step 5. Now, if you have decided your mixing water requirement, if you have decided your water cement ratio, it means your cement content will be decided based on these 2 parameters. If your water cement ratio is 0.62 and your water requirement is 181 kg for every meter cube of concrete, then what should be your cement requirement for every meter cube of concrete? Okay, so it is
291.
how much?
291.
0.9. So better say 292. Because this was kgs of water for every meter cube of concrete. This will be kgs of cement for every meter cube of concrete. Okay? So kgs of cement per meter cube of concrete. Okay? It's important to keep understanding what these numbers actually mean. Kgs of cement per meter cube of concrete. This was kgs of water per meter cube of concrete. Okay? So what has been decided so far? Cement and water. Cement 292 kg per meter cube, water 181 kg per meter cube. What else needs to be decided? Coarse and fine aggregates?
Yes, sir.
Okay. So step number 6 would be, okay, step number 6 would be, I think I can remove this part now. Okay. So step number 6 is about deciding the coarse aggregate. Okay. So coarse aggregate. How much will be coarse aggregate? Okay. So please go to table A. Maybe I can write it down over here. So you go to table A 1.6.3.6. Okay, please go to the table. It is on page number. Same page, 23, page number 23. Okay, so this is the table. On the top of page number 23, you should be able to find. On the top left, it is table A 1.6.3.6. It says volume of coarse aggregate per unit volume of concrete. Okay, so we're not yet deciding the kgs of coarse aggregate per meter cube of concrete. First, we're going to decide the meter cube of coarse aggregate per meter cube of concrete. We can then convert using densities. Okay, so meter cube of coarse aggregate for every meter cube of concrete. We're going to decide this from this table. Okay, so on this table you can see over here we've got the nominal maximum signs. Okay, and what else? And over here you see the finest modulus of sand. Fine aggregate that we're going to use. Okay? In our case, the finest modulus is 2.8. Okay? So this value is 2.80. Okay? And the size is 37.5 millimeters. Okay? Size is in millimeters. 37.5. Normal maximum size of coarse aggregate is 37.5 millimeters, and finest modulus is for fine aggregate is 2.80. So what do you think? What is somewhere over here?
0.7.
0.71.
7.
Okay. 0.71. What is it? 0.71 meter cube of coarse aggregate for every meter cube of concrete. Okay, so this is the meter cube of coarse aggregate for every meter cube of concrete. Okay, now how do we decide? How do we? So if you know the meter cube of coarse aggregate, how will you convert this to kgs of coarse aggregate?
Multiplying by density.
You have to use density, okay? So we have been given this information, dry rodded density of coarse aggregate. You need to understand this term. Dry rodded, okay? Dry rodded coarse aggregate density, okay? So dry means that the coarse aggregate was in dry condition. Okay, dry means bone dry over here. And rodded means it's not the loose density, it's the rodded density. I hope you remember that procedure. Okay, what's the standard that we use? ASTM? Which standard? C29. Okay? This comes from ASTM C29. Okay? And just for your information, this will come from, these two will come from ASTM C. I guess it is 128, and this, for this information, should I recognize these two? This will come from ASTM C127, I'm guessing. Maybe I'm just mixing these two, but I guess it is one of these two for one and one for the other. So, and this is something coming from ASTM C136. So next time you need these standards because you have to do these experiments before starting your mix design for each group. So how do you calculate this term 1600? How was this calculated? Dry mass, dry body mass, okay? Dry the full thing, dry rotting mass over bulk volume. Okay, it's bulk volume. You understand the difference? One is bulk volume and the other is absolute volume. So bulk volume includes the voids between aggregate particles. Okay, that volume includes those. Absolute volume is something related to specific gravity. It does not include the voids between aggregates. Okay, so specific gravity is something about maybe a single particle of that material, single particle of that material. Okay, and for this term bulk volume, and this basically the full name would be bulk dry body density. We can say dry body bulk density. Okay, so it is something we need to understand. So how do we get? So this is how you get this number, 1600 kg per meter cube. So in our case, we know this meter cube of concrete. Sorry, meter cube of coarse aggregate. We gotta find this. Okay, so it is 1600 kgs. Now you need to be very careful. This is 1600. When you say the word kg per meter cube over here means 1600 kgs of coarse aggregate per meter cube of. No, it doesn't mean that. It is what? It's just the density of coarse aggregate. It means every meter cube of coarse aggregate, every meter cube of coarse aggregate weighs 1600 kgs. Okay? So you got to be careful. So 1600 kgs, let me make it more clear. 1600 kgs of coarse aggregate, it makes the sentence long, but I want to make it clear. Aggregate per meter cube of coarse aggregate. And we know the condition, dry and rodded. Okay? And the meter cube is the bulk volume. You walk over here. Okay? So it's basically something, so this is the density you expect in the actual concrete. That's why you get the rodded density. Okay? Now, you know this term, 0.71 meter cube. Okay? Let me make it clear. This was meter cube of force aggregate per meter cube of concrete. Meter cube of force aggregate per meter cube of concrete. So we just working with this term right now. It means when you convert this meter cube of force aggregate to kgs of force aggregate, you are still working for every 1 meter cube of concrete. Okay? So 0.71 meter cube of force aggregate for every meter cube of concrete. If you just put this value over here, maybe um, maybe I could put the value over here. So this is the 1600. So this is the equation. This is the equation. Okay. Maybe I could draw a box over here. This is the equation. That's what this 1600. So this is just the explanation of 1600. Okay. So this is the equation. You know this term bulk volume. So it is 0.71. This is 1600. So what do you get? So the dry volume mass would be. So dry rod is force aggregate content, I would say. Force aggregate content. Content, when I say content of aggregate, water or cement, I usually refer to the kgs of that material per meter cube of concrete. Okay, so when I say water content, I actually say that much meter cube, that much kgs of water for every meter cube of concrete. Okay, so when I say content, it means I'm talking for every meter cube of concrete. So for dry rod force aggregate content will become, so 1600 over 0.71. What do you get? Yeah, I'm sorry about that. Yeah. Yes, multiply. That is 1600 times 0.71. What is 1600? So what is 1600? Yes, so kg is of course aggregate for every meter cube of course aggregate. And this is 0.71 is the meter cube of course aggregate for every meter cube of concrete. Okay, so you know whatever comes out will be for every meter cube of concrete. So now what is the answer now? 1136 kg. And you remember it is for meter cube of concrete. Okay. So we have decided one more ingredient. We're done with cement, we're done with mixing water, we're done with coarse aggregate. Now what is left? Fine aggregate. So for fine aggregate, we actually don't calculate anything. The procedure, I need your attention on this point. The procedure for fine aggregate is based on if I have got certain concrete, so if I know three of the ingredients, I can work out the remaining ingredient by subtraction from the total. Okay, this is the bigger picture. Now, you can work either, so I need your attention on this point. There are two ways to decide the content for the fine aggregate. One is the weight method. So what does that weight method actually mean? In that case, you need to be able to guess the weight of concrete in kgs for every meter cube of concrete. This is the simpler method, by the way. Okay. For example, if I tell you, what do you think should be the weight of concrete for every meter cube of concrete? Kgs, simple words, density of plain concrete, how much? Okay, so when you say 2300, it refers to the hardened concrete in which water is evaporated and it's slightly lesser. But when we talk about fresh concrete, it is slightly higher because the water is not yet evaporated. Okay, so the so we call it fresh density of concrete. Okay, and there is a standard for finding that. I'm guessing it is C30 maybe or C130. I got to check this, but there is a standard for it. Okay, very simple test. Okay, so fresh density of concrete if you can guess that value, okay. For example, if I tell you it is 20, for example, 2350 kgs, 2350 kgs for every meter cube of concrete. So what is going to be the procedure for finding out the fine aggregate? Yes, very right. So you add up cement, water, and coarse aggregate, you get a number. So if you find the difference between this number and the total weight per meter cube, you get your fine aggregate per meter cube of concrete. Isn't it simple enough? But the problem is that it's not really easy to guess with it is possible to guess, and there are some equations to guide you. Uh, so, 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 so the more accurately you can guess that fresh density of concrete, the more accurate is going to be the proportioning. What is the other method? The volume-based method. So I think I can first tell you the volume, the weight based. I like the weight based method. Makes the things quite easier. Takes off a lot of calculations. Okay, so let's work the weight method first, and then I'll tell you how to deal with the absolute volume method. The other method is the absolute volume method. Okay, so let's first work out with the weight method. Okay, so this is the weight method. I can say mass basis. So step number 7. Where is step number 7? Yeah, we're at step number 7. So let's write down a summary of what we have decided so far. Okay, so we have decided. Yes. So where should I put the summary? I think I can put it here. Here. So the summary so far is water was 181 kg per meter cube, and this is the mix of water that you need. Okay. And what else? Cement. What was cement? 292.
Yes, sir.
kg per meter cube. And what else? Coarse aggregate. If I can, I'm writing CA for coarse aggregate. Okay. 1136 kg per meter cube. In all these terms, per meter cube means per meter cube of concrete. Okay. So these are the quantities for every meter cube of concrete. Okay. So it is CA. Now what you need is the fine aggregate. So we are first going to do it on the mass basis. So we need to guess the fresh density of concrete. Okay. Now this is a table. A 1.6.3.7.1. It's on the same page as you are now, 23. Page number 23, extreme right, top right. It says, first estimate of mass of fresh concrete in SI units. Okay, and what do you see in the table? On the left we have the nominal maximum size of aggregate, and again you've got two distinct types of concrete: air entrained concrete and non-air entrained concrete. So I'm going to write only non-air entrained concrete part. So you are in this part, in this column, and so you can end up. So if the size is 37.5 millimeters for our case, maximum nominal maximum size of coarse aggregate 37.5, and non-air entrained concrete. If it is non-air entrained concrete, the estimate is 2410, and this is the fresh density of concrete. Okay.
Okay, sir.
It is per meter cube of fresh concrete. By the way, all these terms are for the fresh concrete. Okay? Did you get it?
Yes, sir.
So can you tell me the value if the nominal height of the aggregate were 19 millimeters?
2345.
2, 3, 4, 5. I hope everybody's getting this.
Yes, sir.
Okay? If they've got a table, it should be consulting the table. Now, so it's simple now. The mass of fine aggregate, therefore, is estimated to be 2410. 2410 minus what? 181 minus 292 minus 1136. Okay? So you get 1609 kgs per meter cube of concrete. So you have decided the fine aggregate as well.
Yes, sir.
I believe it is wrong.
501.
169 is the sum.
801 answer.
Yes, sir.
Okay, it is 801. kg per every meter cube of concrete. Okay? So this is the simpler method, but generally considered to be less accurate because you don't really have the. It's really hard to guess this number 2410. Anyways, it depends actually on several things. What is the most variable parameter in guessing this? What is the most problematic term? I mean, of course, it depends upon that, but if you know that, what else you think will affect that value, 2410? Not temperature. Depends on the operator. Somebody will be pushing the concrete very hard while hardening, somebody else may be like milder. So depending upon how, somebody may use vibrating table. In fact, there are different guidelines that you need to use when you find the fresh density of concrete. They're given in that standard. Okay, I need to see that standard, but anyways, so you better use the same method of vibrations, same method of consolidation that you will be using for your actual mix, okay? Because that way you can get the more. There is one more problem which I think will make make it more confusing rather. That's why I'm not discussing it right now. But I hope you finally get to that point. Anyway, so we've done the mass basis method, and then we need to do the absolute volume basis method.